So let's look at the graphs of some functions we need to make sure we know y is f of x falls to the left and rises to the right. Y is x cubed, falls to the left, rises to the right. Y is x to the fifth, falls to the left, rises to the right. F of x is x squared, rises to the left, rises to the right. F of x is x to the fourth, rises to the left, rises to the right. And f of x is x to the sixth, also rises to the left, rises to the right. Now, when we're graphing polynomials, there are a few things we should notice. Again, remember, A provides our stretch or our shrink. The negative provides a reflection. The plus K is a shift up or a shift down. The minus H is a shift to the left or shift to the right. So let's look at f of x is x cubed plus 1. We want to find the largest open interval where the domain is increasing or decreasing. So the graph is the same as the graph of x cubed, but translated 1 unit up and includes the following 3 points, negative 1, 0, 0, 1, and 1, 2. So we see this is a shift up 1 of the cubic function. It's increasing over its entire domain. So let's look at f of x as x minus 2 to the fifth and find the largest interval for which it is increasing or decreasing. We see this is going to be the same as the x to the fifth function, but translate it 2 to the right. So when you find your points, again, you see it's been shifted 2 to the right, and this is also increasing over the entire domain. Let's look at f of x as minus 1/2 times x plus 3 to the fourth. And when I graph this, it's the same as the x to the fourth, except it's been translated 3 to the left, reflected, vertically basically compressed by a factor of 1/2, and then translated 5 units up. And when I graph this x to the fourth makes it very, very flat here at the vertex. I see that this function is increasing from negative infinity to negative 3 and decreasing from 3 to infinity. Let's look at the behaviors at zeros. Okay, here I have x to the fifth minus 2, and we see how it just sort of, it's very steep and it just crosses right there at the 0. At this 0 right here, this x to the sixth is very, very flat, just like we noticed on the last problem. Here it's shooting x cubed, it's crossing, and it's actually pretty steep. Now, notice at these 4 real zeros, how it's crossing. And here it crosses, but here it bounces, it touches at just 1 point. And here it crosses and changes shape here. So you'll notice here at the x plus 1 where it bounces, that corresponds to a 0 of x equals negative 1. And it doesn't cross the axis like it does when the exponent is 1 or when the exponent is 3. It turns out that when you have a multiplicity of 1, when you fully factor it and you look at the multiplicity of the 0, when the multiplicity is 1, then it's going to cross the axis. All right. When the multiplicity is even, the graph bounces at C. It just comes up and kisses it. It doesn't cross it. Now, the graph crosses and can be a little bit tangent to the x-axis at 0 if it C is a 0 of odd multiplicity greater than 1. So you have this kind of squiggle that occurs. It's not a nice straight line. Now, a polynomial of degree n has at most n minus 1 turning points, which a turning point, think of it as a maximum or a minimum. Let's look at the end behavior. Um, Always look at your highest power of your polynomial. This is always going to determine your end behavior. When your polynomial is odd and the a is positive, then think about this. As x goes to positive infinity, the function is going to go up toward positive infinity. As x approaches negative infinity, the function goes toward negative infinity. So we're going to use graphically, we're going to symbolize it with the arrows. So we're going to say it is down and then up, because as x goes to negative infinity, it goes down, and as x goes to positive infinity, it goes up. When a is negative, those, of course, are going to switch. So it will go up and then down. So whenever you have an odd polynomial, then the end behaviors will be opposite. One will be up, one will be down. When n is even, then the end behaviors are going to be the same. They're both going to be up or they're both going to be down. So when a is positive, it's going to be up, up. And when a is negative, it's going to be down, down. So let's just determine the end behavior of our polynomial. F of x is minus x to the fourth plus 2x squared plus x minus 8. Remember, I don't care about anything but this leading coefficient. Since a is -1 and is negative, and n is even, it's going to be down, down. What about g of x is x cubed? And I'm not even going to read the rest, because what do I really care about? All I care about is that leading term. A is 1 and it's positive. G is odd. So it's going to be down, up. What about negative x to the fifth? A is negative and it's odd, so it's going to be up and then down. Now, what about k, which is x to the sixth? A is 1 and it's positive. 6 is even, so it's going to be up, up. Suppose you want to graph a polynomial. The first thing you want to do is find the real zeros and graph your zeros. Then you want to find your intercepts, f evaluated at 0. That's always a good point to plot, and it's easy to find. And then you use your end behavior to determine whether it crosses, bounces, wiggles as it crosses the x-axis. And then you pick extra points as you need. So suppose I want to graph 2x cubed plus 3x squared minus 11x minus 6. So the first thing you need to do is find all of your zeros. So you can use the rational root theorem and see that you can have rational zeros of possible plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, or plus or minus 3. You can use the remainder theorem, and you do have to do a bit of trial and error here, to see that x equals 2 is a 0. All right, so this gives you your second polynomial. So x minus 2 times 2x squared plus 7x plus 3. So we can factor the 2x squared plus 7x plus 3 into 2x plus 1, x plus 3. So now we can find our zeros by setting each factor equal to 0. So I have the zeros 2, -1/2, and -3. Now we want to find f of 0. F of 0 is -6, so we can graph that point as well. Now we want to look at the x-intercepts and divide it into the intervals and substitute in values to give us an estimate here. So from -infinity to -3, my test point is -5. So the value of f of x at -5 is -126. So this is going to be negative values. You can plot that point. At -2, it's 12. And so it's going to be above the axis at that in that interval. At 1, we have a value of negative 12. So the function is negative that point. It's going to be below the axis. And then the last point we're going to pick is 3. So we're going to test the value of f, and we get 42. And so the function is going to be above the axis from 2 to infinity. So if I plot my zeros, um, I know that 2x cubed is going to have it's the coefficient's positive, the power is negative, so I know it's going to be down and then up. The multiplicity of each 0 is 1, so it's going to cross as it goes through. All right. And if you have picked points close enough, we're not going to get too much into the actual maxes or mins just yet. The general shape should be something like this squiggly snake-looking thing here. Suppose I want to graph x plus 2 cubed times x minus 1 squared. Now, we've already found the zeros. It's kind of given to us. The zeros are negative 2 and 1. Negative 2 has multiplicity 3, so we know we're going to squiggle. And 1 has multiplicity 2, so we know it's going to bounce there. You plot your 0, 8. All right. So we know we've already discussed the multiplicity of our terms. You can graph some test points. All right. So when I graph it, all right, there's my intercept. I see that it's n is 5. So the coefficient is positive. So I know it's going to be down, up. So once I graph this 0 right here at x equal 1, I know it's going to bounce at this point right here. So it's going to be going up, and then it's just going to kiss it right there. I've got this point, so I know it's got to go through that point. At negative 2, I know it's going to cross it, and I know it's going to squiggle. So it's going to go up, come down, squiggle, and I know it's got to go down. Let's look at the relationships among the x-intercepts, the zeros, and the factors. And the answer is they're all the same thing. If C is a 0 of f, then C is a solution of f of x equals 0. And x minus c is a factor of f of x. These are all incredibly related concepts. Once you've found one, you've actually found them all. The intermediate value theorem says that if I have a polynomial of real coefficients, and there are numbers a and b such that f of a and f of b have opposite signs, so one is positive, one is negative, then the function, nice and continuous, it's got to have a 0 in that region somewhere. The intermediate value theorem doesn't tell you where it is. It just says it's in there somewhere, because at one point it's positive and then it's negative. So let's use synthetic division and a graph to show that f of x equals minus x cubed plus 2x squared minus 4x plus 5 has a real 0 between 1 and 2. So use synthetic division to find f of 1 and f of 2. When I evaluate f of 1, I see that the functional value is 2. And when I evaluate f of 2, I see it's negative 3. By the intermediate value theorem, there has to be a real 0 between 1 and 2 because f of 1 is positive and f of 2 is negative. And indeed, if I were to graph this on a graphing calculator, I would see that there is one, and I really don't want to try and pick what it is. It looks ugly. Boundedness theorem says, let f of x be a polynomial of degree greater than or equal to 1 with real coefficients and a positive leading coefficient. If f of x is divided synthetically by x minus c, if c is positive, all the numbers in the bottom row of the synthetic division are non-negative, then f of x has no zero greater than c. If c is negative and the numbers in the bottom row of the synthetic division alternate signs, where 0 is either positive or negative, then 0 has no 0 less than c. Ooh. So let's show that this has no real zeros greater than 1. So f of x has real coefficients, and the leading coefficient is 1, and that's positive. So to apply the boundedness theorem, we need to divide f of x by x minus 1. When I do synthetic division, I see I get 11692. So all of these are positive. Since 1 is positive and all the numbers in the last row of the synthetic division are non-negative, f of x has no real zeros greater than 1. So let's show that f of x is x to the 4th plus 5x squared plus 3x minus 7 has no real zeros less than negative 2. And you look at my leading coefficient is 1. It's positive. So by the boundedness theorem, I need to divide by x plus 2. Now, when I look at my bottom row, I see that the numbers alternate in sign, positive, negative, positive, negative, positive. So since negative 2 is less than 0 and the numbers in the last row alternate sign, then f of x has no real zeros less than negative 2.